This video is made to cover Vsepr theory, which we talked about in class, which is how we predict the electron geometry and molecular geometry of a molecule from the two-dimensional structures that we've been drawing on paper. So basically, this is a way of predicting the 3D shape of molecules based on our 2D drawings. And the notes are all going to be taken care of on page 3. Then I'm going to help you through the practice problems on page 4 to actually apply this process, and then it shouldn't take you much longer to finish up pages 5 and 6 like we did in class. So, first things first, what is Vsepr theory? Well, Vsepr is an acronym that stands for valence shell electron pair repulsion. And while that might seem like a lot, all that means to us is that the valence shell electrons, really just any electrons, are going to be repelling each other. And we use this idea of our electrons wanting to be as far apart as possible to predict these shapes, these geometries. Because if they want to be as far apart as possible, then two groups as far apart as possible are going to make a linear shape. Three groups spreading out perfectly equidistant is going to be more of a triangular shape. So we can use that in order to predict these geometries. Now, there are technically two different geometries we're going to be discussing. The first is called electron geometry, and that's where we consider all of the electron areas around an atom in a molecule and what shape all of those electrons take. So we have two different types of electron groups, our bonds and our lone pairs, also known as non-bonding electrons. And so in our electron geometry, the shape that we're considering and naming is the shape made from bonds and lone pairs together. In fact, we're going to be adding up the number of those groups, counting them, adding them up to see what shape this is going to make. The other type of geometry is called the molecular geometry, and this is the true molecule shape if we could actually see it with our eyes. And the difference here is that we only care about and count the number of electrons that are in bonds. So we don't care about the lone pairs because lone pairs we draw those as dots normally to represent two electrons that aren't in bonds. They're just floating around that specific atom. Well, we can't see electrons. They're too tiny and they're moving way too fast for us to ever pin them down. So we don't actually see them. So while they do repel the other electrons in the bonds around them, they would never be seen even on a molecular level. So we have these two different names for when we kind of pretend like we can see the lone pairs, and then the name the molecular geometry, which is really the shape that this takes up if we were to actually see it, bonds only. So we'll revisit this idea when we actually start going through some of those examples. We'll also come back to these steps that it says to go through when we start doing some examples, because really the first thing that I want you to do is be able to look at this table that we have down here and understand where all of these names come from. So that's where we're going to start, not with looking at structures and coming up with these names, but with what these names even mean and where they come from. And there's a lot of information in this table, and I think it'll help you to focus more on the relevant information. If you draw these two bolded lines in where I have these purple lines, you'll notice that I've put those between the different numbers of total electron groups here. We have 2, 3, or 4 that we're going to be concerning ourselves with. And by putting these lines between those, we kind of get to see the shape families. There are some that are kind of related, that have some commonalities, but that are somewhat different as well. So those lines kind of help you see those families, and how they're related to each other will be a lot clearer if we look at them kind of separately. So that's where I'm going to be starting, is looking at the total electron groups around a central atom. So I'm going to cover up these other columns for right now. Please don't cross these out or scratch these out. They're important information. I just want to focus your kind of attention for a little while just on the total electron groups and the electron geometry that goes with them. These total electron groups, and we don't care whether it's bonds or lone pairs, because remember, in our electron geometry, we count both of them and put them together in order to come up with the shape name. So this is technically the number of groups outside a central atom. Our central atom, no matter how many groups are around it, is always going to be in the center of our shape. So the shape itself is going to be determined not by the total number of atoms, but by the total number of atoms outside of our central atom. As you can see here, with 3 atoms outside my central atom, it's going to be kind of sort of triangular. And I'm not even trying to draw this super correctly. So we're going to get to that. I'm actually, instead of trying to make my own drawings, going to use balloons as an example. And in class, I actually held up balloons of different colors to help you see some of these changes. Here, I'm just going to be able to use some pictures of balloons, but especially if you have some at home and you didn't get to see me play around with them in class, you just need 4 balloons, and then you can kind of tie them together in order to see these relationships, because it's a simple idea that things like to spread out. They don't like to be squished together, and balloons are going to act and react the same way that electrons do. So here, visualize our central atom as the central knot tying together these balloons. So here, we're looking at 2 balloons, meaning 2 electron groups, bonds or lone pairs, doesn't really matter. And those 2 groups, if they do spread out as far apart from each other as possible, are going to make a line, a linear shape. So that's what we call the electron geometry of a molecule with 2 electron groups around the outside. Pretty simple. Notice the bond angle over here also matches up with our understanding of lines from geometry. Because this is a single line through that central atom and the ends of each of the bonded atoms, for example, then the distance, the number of degrees from one bond to the other is 180 degrees, half of a full circle, half of a full 360 degrees. When we add another balloon tied to our central atom, tied to that central knot, you shouldn't be surprised that with 3 total balloons, we're going to end up with a kind of triangular shape, and much better drawing than I had made before. Now, you'll notice this isn't called a triangle. Of course, chemistry is going to make our names a little bit special and unique. We use the word trigonal, and then we also add in this word planar, because this is a flat triangle. If I turned these balloons on their side and you looked at it right at that central knot, there would be a single plane that could cut each of our balloons in half, kind of like we looked at this side. And it could cut the central atom, that knot, and all of the balloons exactly in half with a single plane. So we are going to see another kind of triangular shape later that we will still call trigonal, but it's not going to be a flat triangle. So it's important that we can tell the difference between them. And just like with our 180 degree bond angle for 2 balloons, 2 electron groups, when I have 3 groups around my central atom, then our bond angle ends up dividing that full circle into 3 pieces, and that means that the bond angle between any 2 bonds is 120 degrees. Now, if we tie a 4th balloon to the center, you might think that this would make a square, but it actually wouldn't. And this is where, if you have 4 balloons at home to play with, then go ahead and blow them up, tie them together, and you'll see that they don't like to squish together into a square. You can make them do that, but if you wiggle them around, move them around, even just pick them up, nudge them, then they're going to want and try to turn into this tetrahedral shape. And the reason for that you can see based on the bond angle. Here in this square, each balloon only gets 90 degrees of space because they're 4 balloons sharing the same plane, the same 360 degrees. So they would only get 90 degrees of space. Now, I probably can't draw this angle very well, but this tetrahedral geometry gives each balloon 109.5 degrees of space, about 110 really when it comes down to it, which is 20 degrees more space than they would have if we squished them into that flat square. So that's why our balloons and our electron groups are going to prefer this tetrahedral shape instead of this square. And tetrahedral, while it is kind of a scary, weird word that we do have to work on memorizing, hopefully that tetra prefix is still stuck with you from our naming unit, where tetra was a prefix we used for something that had 4 atoms of some type in a covalent compound. So we're still dealing with covalent compounds here, just their shapes. So tetra is the appropriate prefix that we're going to use to describe this shape. So that is our electron geometries. There's only 3 possible options that we're going to be talking about. These are as complicated as we're going to let our molecules get. And so now what we're going to do is start talking about the molecule geometry. And well, what if these are this many bonds or this many lone pairs in different variations and different combinations? But when we look at these, and I uncover the rest of the table, notice that no matter what is happening with our bonds and our lone pairs in each of these situations, the total is still going to be adding up to the total number of electron groups. So these are just variations on these shapes that we've been seeing already for this electron geometry. And what if one or more of those groups happened to be a lone pair and was thus kind of sort of invisible to our eyes? And the most different variations that we have here are going to be in our tetrahedral molecule. So we're going to start with that one that we just got to. And you'll notice our first line of this tetrahedral group is, what if we had 4 bonded groups and no lone pairs? Well, that is equal to 4 total electron groups. And when we think about how many things we can actually see there, since our molecular geometry, we can only see bonds, we still see 4 things, 4 solid atoms bonded to that central atom. So what we're seeing for our molecular geometry is the same as what we are seeing for our electron geometry, 4 groups, which means that it will be tetrahedral. So when we have no lone pairs, there's no difference between my electron geometry and my molecular geometry, because if there's no lone pairs, then we're just left looking at bonds in the electron geometry, which is what we're looking at in our molecular geometry anyway. Now let's imagine like one of these groups is a lone pair. Now I'm going to color it in, or kind of cover it up with this light blue highlighter color, because it is still there. It's just when it comes to the electron geometry, we consider it, and in the molecular geometry, we do not. We can't see it there. So if I think about it, I'm only going to be seeing 3 things, 3 bonded groups. And then that should hopefully make you think, well, that's going to be triangular, trigonal, which it is. But even though we can only see those 3 bonded atoms, and that lone pair is invisible to our eyes now, it is still there, and it's still having an effect on those 3 bonded atoms. And if you look at this, these 3 bonded atoms are at a slight angle here. They're not a flat triangle. I can't pass a single plane through the middle of all of them, and any attempt to pass a plane through them is not going to pass through the central atom, and it's not going to exactly cut each of these in half. So instead of calling this trigonal planar, we call it trigonal pyramidal. Its electron geometry is still tetrahedral, because if I could see all of the electrons, that would act as a tetrahedron, and I would see 4 things, it's tetrahedral. But as soon as we talk about the molecular geometry, where those lone pairs are invisible, I'm only seeing 3 things, but those 3 things that make a triangle are going to be pushed towards each other by that invisible lone pair, making it a pyramid. Notice in the bond angle, this is probably going to be slightly less than 109.5 because of the downward pushing of that lone pair on the other ones is slightly greater than the push of the electrons in a normal bond. But for our purposes, we just want you to recognize that this is still having a tetrahedral electron geometry, so that bond angle would still be about the same as our tetrahedral molecular geometry would be. Then, if I have two of these groups are as lone pairs, two of them as bonds, we're still dealing with 4 total electron groups, which is why it's still tetrahedral electron geometry. But if we go ahead and blank out 2 of these balloons, that means I can only see 2 bonded atoms here, 2 balloons. And you might think, oh, 2 balloons, if they want to spread out as much as possible, will make a linear shape. And that would be ideal if there were only 2 balloons here. But as you can see from the 2 balloons that I haven't scratched out here, they're not able to form a nice straight line because there are still those lone pairs pushing on those bonded atoms. So even though those 2 balloons want to be a nice straight line, they can't. As soon as they get pushed on by a lone pair or 2, then that line becomes bent, which is exactly what we call the molecular geometry of this tetrahedral electron geometry, when 2 of those are lone pairs and 2 of those are bonds. So we wish we could be aligned because we see 2 things, and we should be thinking linear when we see 2 things, but we need to recognize with the molecular geometry specifically that sometimes there are some invisible lone pairs that we're not seeing that are having an effect on that shape, either to make our triangle more of a pyramid or to make our line a little bit bent. So that's our tetrahedral variations, the tetrahedral family. Now let's go and look at the 3 electron group family and the variations that it can have. So with fewer total electron groups to work with, we have a little bit less variation possible. And our first row of our 3 electron group section is, well, what if all 3 of those electron groups are bonded atoms, no lone pairs? That means in both the electron geometry and the molecular geometry, we're seeing 3 things. 3 things should make us think trigonal. We always have to check, is this a flat triangle or is it a pyramidal triangle? Is it a little bit bent up by lone pairs? And here we have no lone pairs, so this is trigonal planar for both of our geometries. Now, what if one of my balloons was a lone pair? What if I only had 2 bonded atoms and 1 lone pair? Still gives us our 3 total electron groups, so we still have our electron geometry being trigonal planar. But then, if I'm talking about my molecular geometry, then I'm only seeing my 2 bonded atoms. And I should be thinking, 2 balloons, 2 electron groups are going to try and be a nice straight line. And it should be linear. But just like what we saw with the tetrahedral geometry, as soon as I have a lone pair, even if it's just 1 lone pair on those 2 bonded groups, then my line can't be nice and straight, linear. This is going to be bent. So we have this bent geometry name again, and the similarity is that there's 2 bonded atoms, 2 groups, but then we have some lone pairs on it. The only time we have a truly linear molecule is when we have 2 bonded atoms and no lone pairs on them. And we don't actually have any variations of our 2 bonded atoms, because as soon as one of these becomes a lone pair, then we just have an atom bonded to another atom with a lone pair on one side. So it doesn't have a bond angle, and it doesn't really fit in our table nicely, but we will see some molecules like this, and I'll show you what to do with them a little bit later. But in general, if you see 2 electron groups, 2 bonds, that's automatically going to be linear, unless, of course, it is bent. So always be on the lookout for those lone pairs. That's one of the reasons it's so important to make sure you draw your structures right, so that you can see if you have lone pairs on that central atom or not. So at this point, we're ready to start looking at the practice problems on the next few pages. And so I'm just going to actually remind you of this chunk of information, these steps right above the table that we're going to put into effect now that we're moving on to actually do these practice problems. So our first step in figuring out our electron and molecular geometry is always draw the Lewis dot structure. And then we're going to count the areas around the atom, paying attention to whether they're bonds or lone pairs. In fact, I put a little place for you to write that information next to your structures on the next few pages, just to help reinforce we got to count these things separately and be always thinking, what can I see? The electron geometry, I can see my bonds and lone pairs. In my molecular geometry, I only see bonds. And then once you've got those numbers in front of you, if I'm seeing 4 things, that's tetrahedral, 3 things trigonal, have to figure out whether it's pyramidal or planar, but that's fine. And then 2 groups, I should be thinking linear, and that could be straight plain linear, or it could be bent if I have any lone pairs on that line. So you just have to be kind of thinking of those shape names, where they come from, and everything else is just about drawing the structure correctly and counting the number of bonds and lone pairs on the central atom. Quick note about that central atom being what we're counting things around. Imagine I have 3 balloons tied together. That's a trigonal planar shape as we know it. But then maybe imagine that I have one special balloon that is a little animal balloon with ears on it and maybe some cute little like nose and mouth features sticking out. That fancy balloon with all of that stuff sticking out of it at its end doesn't affect the fact that tying these 3 balloons together is still a trigonal planar arrangement. So when we're talking about and counting our bonds and our lone pairs, the only ones that matter are the number of groups, the number of electrons around the central atom. Everything else is just kind of decoration and fluff around the outside of the shape that's made around the central atom. So those are the only bonds or lone pairs that we care about. So question number 1 on the next page, page 4. I'm going to draw CO2 for you because we've drawn it before and I just want to help you analyze a structure, not ask you to draw out all of these structures on your own over and over again. So because CO2 has 16 valence electrons, if we single bond everything together, we're going to run out before carbon is happy, which means that we have to move 2 of those lone pairs in to make them double bonds. And each of those is a double bond. It's twice as strong, yes, twice as many electrons, shorter, lots of different properties, but it's still a single bond. Those aren't 2 ropes or chains separately holding these together. It's an individual bond there. It's just called a double bond. It's still 1 bond though, so that means that we have 2 bonds around our central atom, no lone pairs around the central atom. Those lone pairs around the oxygens don't matter for our shape. And since I'm seeing 2 things for my electron geometry, 2 bonds, then that means that this is going to be a linear shape. And our molecular geometry, I only see bonds. I still have 2 bonds, so my shape is still going to be linear. Once again, reminding you, if we have no lone pairs in our central atom, that these names should be the same. Not too bad so far, I hope. This drawing automatically just kind of looked linear, so it's a pretty decent guess as long as you draw your structure correctly. Here with H2O, we only have 8 valence electrons to work with, but since H only needs 2 and it gets them from those single bonds to the oxygen, then it's happy. Remember, we never ever put dots or double bonds to H's. They're happy and full with just 2 electrons. So here in our H2O structure, we have 2 bonds, and then we have 2 lone pairs directly on our central atom, which means that when we're talking about our electron geometry, when we see bonds and lone pairs, that means we're looking at a total of 4 things here, which means that our name is going to be tetrahedral. In my molecular geometry, where I only see bonds, though, I only see those 2 bonds. So my brain should be thinking linear, but we always need to remember to check on our molecular geometry if there are any invisible lone pairs we're not seeing, and there are. So even though I have drawn this and it kind of looks like a nice straight line, the way I've drawn this water molecule, I can realize this is really going to be a bent structure in three-dimensional space. So that's our water. Moving on to CH4. Here again we have 8 valence electrons to work with. C is going to be in the center, and as soon as we single bond all of those H's around it, then we've used all our electrons and everyone's happy. So we have 4 bonds here, 0 lone pairs. Electron geometry, I see all of my groups. 4 plus 0 is 4. And if I'm seeing 4 things, that is always a tetrahedral geometry. In my molecular geometry, I see 4 bonds only, but it's still 4 things, so that's still going to be considered tetrahedral. Now back up at the top of the page with CCl4, we have 32 electrons to work with. Putting C in the middle with our 4 Cl's around the outside. Single bonded is all that we need after we put all the rest of those dots out to fill up those Cl's. So with this being our final structure, we see 4 bonds. And even though we've got a lot of dots in this structure, there are no lone pairs around the central atom. So that is still 0 lone pairs here, which is the exact same breakdown of our CH4. So just like with CH4, where we have 4 groups around our central atom, then that electron geometry is tetrahedral. I have 4 bonds around my central atom, so my molecular geometry is tetrahedral as well. So I wanted to show you these examples where the structures are different but similar enough that we end up getting the exact same geometry names. Here with our NH3, we have 8 valence electrons to work with. Put an N in the middle, single bonds to everything around it. We have 2 electrons left over to give to nitrogen to hold on to help complete its octet. So looking at nitrogen, we have 3 bonds, 1 lone pair. That means in my electron geometry, where I see all of those electrons, it doesn't matter what they are, I'm looking at 4 things total, which means that this is also tetrahedral for our electron geometry. But here, we only have 3 bonds. So in my molecular geometry, I'm only seeing 3 things, and my brain should be thinking of that weird triangle word we use, trigonal. And then I have to ask myself if this is going to be a flat triangle or a pyramid, and this one is going to end up being pyramidal because we do have that lone pair on our triangle. So this is trigonal pyramidal for our molecular geometry. 1 left on the page, and HF isn't that bad to draw out. We only have 8 electrons to work with, and then H and F, single bonded, gives all the rest of those electrons to F. But as soon as we start to analyze the bonds and the lone pairs, well, I only have 1 bond there, and kind of depends, our lone pairs, whether I look at my H or at my F. And this is the first time that's happened, and you might realize suddenly, wait, I never really bothered with finding a central atom. It was just H and F. Technically, there is no central atom here, so I can't quite decide which one to count from, and this molecule could leave you really confused and for how simple this molecule really is. And the answer to this problem actually comes from the bottom of the previous page. We kind of skipped over this single sentence here because these are the simplest molecules. They have a really simple answer to them. Anytime we have a diatomic molecule, whether they're the same atom like Cl2 or different atoms like HF, we are going to call their electron and molecular geometry linear diatomic. By having a molecule like HF, where we just have 2 atoms bonded together, our electron cloud might be a little bit bigger around that F, but it's still going to be a linear shape. So we don't really care at this point how lopsided our line is. This is just a line that's made out of 2 atoms. 2 points determine a line. That's the only shape that it can be, even if it might be a little lopsided on some of its variations. So both our electron geometry and molecular geometry will be linear diatomic here, and any other time where we only have 1 bond in our molecule. Soon as you end up counting that one bond, it doesn't even really matter how many lone pairs there are because it might be around one atom or both. As soon as you see a single bond, the only bond you have in that molecule, then this is going to be linear diatomic for both of our geometries. Now, this linear is a very slight variation on our just plain old linear, but remember, molecules like CO2 are what we would call linear, just plain linear, and notice that they have 3 atoms in them. And it's just going to be a slightly different shape than these linear molecules that are only made out of 2 atoms, which is why we add that extra little variation on there to differentiate between these 2 shapes. So, linear, linear diatomic. Now, this is the last one that I'm going to do with you. It's your job to finish up pages 5 and 6, but there are 2 different structures that I actually don't want you to have to draw and analyze because we put them there to do that polarity and IMF thing that we're going to do later. They don't actually have very good specific shape names. And the first one is CH3OH. This is on page 5, number 11. And what I want you to do first is just cross out the bonds, lone pairs, electron geometry, and molecular geometry. We're not going to do any of that for this structure, and that's why I'm drawing the structure for you to help you later when we need to do this stuff, but I don't want you to try and take my structure and then start analyzing it, because this wouldn't fit very nice and neatly into any of our groups. And if you are curious about how we would classify this shape, then come talk to me about this in class. It's not something that everyone needs to be able to do. The other one that we're going to look at together and cross out the bonds and geometry words is on the next page, page 6, C3H8. Go ahead and cross out all of this. Not the polarity and IMF stuff, we still need that. And then do a quick sketch of this molecule there on your paper. This will help you later when we discuss polarity and IMF, but not something that I would want you to worry at all about for those geometry names that we just talked about. So go ahead and finish up the rest of these 2 practice pages so that you are ready for our notes on polarity and IMF next class.